Hi Chem Peeps, this is video 4 of Hess's Law under thermodynamics, and this problem actually is a little more complicated than what I did with my first two examples. So let's read the problem, break it down, and solve this. In this problem it says calculate the standard enthalpy of formation of butane, which is C4H10 from the data below. The first reaction, they give us the formation of carbon dioxide and its enthalpy. The second equation, they give us water, formation of water and its enthalpy. And they say the energy enthalpy of combustion of butane and its enthalpy. So let's write a reaction for that enthalpy for combustion of butane. So let's, when you combust something, you're taking that compound and burning it in oxygen. So we're going to have C4H10 and we're going to burn it in oxygen. Oxygen's diatomic, so there's two of them. And combustion forms carbon dioxide and water. Now, to balance this equation, we are going to need 4 CO2s because there's 4 carbons on the reactant side. We need 4 on the product. We need 10 hydrogens to match the reactant side, so I need a 5 here. And that gives us 9 oxygens on the reactant side. Therefore, I am going to multiply this oxygen by 9 halves so that I get 9 oxygens. Therefore, I'm keeping to the 1 mole that the enthalpy is stating here, kilojoules per mole. Okay, so I have 3 reactions here. Now, I want to find a reaction. And what reaction is it we're trying to find? Well, we want to know the formation of butane. Well, butane is made up of carbon and hydrogen. So I'm going to take carbon in its solid form, and I'm going to combine it with hydrogen in its gaseous form to form C4H10. And I want to know the delta H of formation for this. What is this value? Well, first of all, I need to balance this with 4 carbons, and I need 5 hydrogens. So this is what we're trying to solve for with using these 3 reactions in Hess's law. So let's look at what we're trying to achieve here. First of all, looking at the reactions that were given, we want to have the butane, C4H10, on the product side. But if you look in the given reaction, it is on the reactant side. So this reaction must be turned around when we finally write it in Hess's law. So I must turn that around. What else do I need to do? Well, I need to have the carbon on the reactant side. Well, it is on the reactant side in both the desired reaction and what we have to work with. But I need 4 of them. So I'm going to have to multiply this equation by 4 so that I'm going to get what I need. And finally, I need my hydrogen, 5 of them, found on the reactant side. And it is found on the reactant side, but I'm going to need 5 of those. So let's rewrite these 3 reactions in such a way that we should come out with our desired end result here. So for the first reaction, we're going to keep it in the same format, but we're going to have to increase it. So when I multiply by 4, I'm going to have to multiply the equation by 4 also. So I'm going to have 4 carbons plus 4 oxygens, and that's going to give me 4 carbon dioxides. And my delta H is still going to be the negative value, but it's going to be 4 times that negative 393.5. Okay. Second reaction, I'm going to keep it in the direction that it's at, but I need 5 of them. So I'm going to have 5 hydrogens plus 5 halves oxygen gives me 5 waters. And my delta H is still going to be a negative here, but I'm going to take 5. I don't know why my pen gets like that. I'm going to take the 5 times the negative 285.5 kilojoules. Okay, now my last reaction, we said we had to turn it around. So let's go ahead and do that. So I'm going to have 4 CO2 plus 5 waters. And technically, I should be putting the states of matter with the reaction here, but I'm being lazy. I hope it does not burn me. Okay, so we get butane plus 9 halves oxygens. Okay, and the heat, since I turned it around, my delta H is going to be a negative of whatever I had, so now it's going to be a positive 2,877. Okay, now technically, because I have written this out, I should have things that simplify out. So let's look down through the equation. The first thing that I'm going to do here is I'm going to combine these. I have 4 oxygens plus 5 halves. That's actually 9 halves. And so this entire section is going to cross out with this over here. Okay, perfect. I have 5 waters and 5 waters, 4 CO2s and 4 CO2s. And what is remaining? Sometimes when I have a lot going on here, I circle what's remaining and make sure it's going to match what I desire, and it's going to. So let's go ahead and add these reactions together. I'm going to get 4 C's plus 5 hydrogens produces C4H10. And that is the desired reaction that we wanted. So the heat of formation of this is going to be the sum of these 3 reactions. So let's go ahead and add those together. Multiply and add, because we have a lot of math there. So when we do that, we're going to come out with a negative 122.5 kilojoules for this problem. This is beautiful to me. This is Hess's law at its finest. I hope this helps you with thermodynamic questions. My next videos are going to be on entropy and Gibbs free energy. Check me out at YouTube and TikTok at Chem's Chem Chats.